Okay, so when we last left off, we discussed the idea of isotopic abundance. Now we're going to look a little bit into how the percent abundance of different isotopes of an element affects and determines the average atomic mass of that element. So reading the periodic table, one of the central pieces of information given in the periodic table is this number below your element symbol called the average atomic mass. Now, the mass in the periodic table does not match an exact isotope. It's not the mass of any given isotope. It is the weighted average of the mass of all isotopes, accounting for the percent abundance of each isotope of that element in nature. So in shorthand, you can write the average atomic mass as the sum of the mass of the isotope times the percent abundance over 100. Now this sum just means you add each of these terms for each isotope together. So if we're writing this out for a 3-component system, the average atomic mass would be the mass of isotope 1 times the percent abundance of isotope 1 over 100 plus the mass of isotope 2 times the percent abundance of isotope 2 over 100 and so forth. So you essentially take the mass of each isotope, multiply it by its percent abundance, and add it together. Okay, so let's show an example as to how to calculate the average atomic mass. How do we go about calculating the average atomic mass? So for example, chlorine has 2 naturally occurring isotopes, chlorine 35 and chlorine 37. And the percent abundance of chlorine 35 is 75.78. The percent abundance of chlorine 37 is 24.22%. So if we want to figure out the average atomic mass, we would take the atomic mass of chlorine 35, which is 34.97 AMU, times the percent abundance, which is 75.78% over 100, plus the mass of chlorine 37, which is 36.97 AMU, times, times the percent abundance over 100%. And if we punch this into our calculator, our average atomic mass is equal to so this first term is 26.500266 AMU. You don't want to truncate digits. So if we add both of these terms together in one line in our calculator, we get 35.45 AMU for our total average atomic mass. Does this example make sense to everyone so far? Any questions on this example?
I want to make sure I calculated right. The first part was at 26.500266? Or what was the answer for the first part?
This first part, you get 26.500266.
Okay, and we leave it like that, correct? We don't,
Yes.
okay.
I entered it all as one line in my calculator because you
Mhm.
don't want to introduce rounding errors by truncating digits. Does that make sense?
Yes, thank you.
Any other questions on this example? If not, let's now open up our problem solving session 2.13 and let's work on calculating the average atomic mass of boron. So the four sig figs were constrained by the number of significant figures in both our atomic masses and our percent abundance. We have 4 sig figs each, so our answer should have 4 sig figs. Did that answer your question? Yep, exactly. You still follow sig fig rules for the calculations. Okay, so let's take about 3 minutes to work on the following example, and don't be shy to message me with your proposed response using the chat feature or via the Canvas quiz app. And if you have any questions, don't be shy to message me or unmute and ask that question. So let's try to get a few responses in the chat and then we'll discuss momentarily. It's 20 and 80 separately. You plug in the percent abundance of each isotope and you multiply the mass of each isotope by the percent abundance of that specific isotope. It's two parts to the same problem. So it's two different calculations that you add together to get your average atomic mass. Perfect. You round based on the sig figs of your percent abundance and the sig figs of your average atomic mass. So you follow the sig fig rules based on multiplication and then the sig fig rules for addition and subtraction. So let's spend about another minute on this problem, minute to minute and a half. Let's try to get a few more responses via Canvas and the chat, and we'll discuss momentarily. Any other questions? We'll discuss in about another 30 seconds. So let's discuss this problem. So first and foremost, the atomic mass or the average atomic mass is equal to the mass of isotope 1, which is 10.0129 AMU, times the percentage of isotope 1 over 100%, plus the mass of isotope 2 times the percentage of isotope 2 over 100%. Punching this into our calculator, one thing I just want us to note is after the first step, let's just check the Sig Figs in our number for the first step. So after the first step, we get 0.2005. Okay, and notice based on multiplication, our answer should have 4 Sig Figs. Okay, perfect. So we're just doing this for Sig Fig bookkeeping. I'm going to enter everything else as a one line, but I'm just showing which two numbers we're adding together, so that way we can write our Sig Figs properly. So for the second part, we'd get 8.8072. We round it to 4 Sig Figs, and that would be 8.807. Okay, adding each of these numbers together. Punch this into our calculator one more time. We have 10.0129 times 20 over 100 plus 11.009 times 80 over 100. And when we add both of these numbers together, we get 10.8097. Now, we're asked to round our number. In this case, when we do an addition operation, we care not about the total number of Sig Figs, but the number of decimal places. And we round to the least number of decimal places, which is 3, which will give us 10.810 AMU for our final answer. So just make sure you're following the Sig Fig rules for each step in a calculation. So first,
are we measuring the Sig Figs from the natural abundance percentage? Is that why it's 4 Sig Figs?
So first, when we multiply our numbers together, multiplication, we care about the least number of significant figures. The percent abundance has 4. The mass has 6 sig figs. So we take the least number of sig figs, which is 4. Each of our two answers, we write with bar notation for 4 sig figs. When we add these numbers together, we don't care about sig figs, we care about decimal places. And as a result, when we add them together, we then have to round our number to the least number of decimal places, which is 3. Does that make sense?
I don't see the 3 decimal places though. Where is that coming from?
The 0.2005 and the 8.807. When we add them together, this 8.807, if we're accounting for the fact that we only can carry over 4 sig figs, then the 7 by bar notation is the last significant digit. So when we add these two numbers together, looking at the number of decimal places that have significant digits, the third decimal place in 8.807 is the last reported significant digit in a decimal place. That's why when we add these two numbers together, we retain 3 sig figs. Does that make sense?
No, like.
Is there a part I can elaborate on?
Yeah, how is it the 3 though? Like, how is it 3 decimal places? That's a part I don't get.
So like looking at this first calculation, we need to report a number with 4 sig figs. So 8.807, 2, the 2 is not significant. So we put a bar over the 7, and that tells us the 7 is the last significant digit. So we can pretend functionally like this 2 doesn't exist when we're counting decimal places. So how many decimal places does this number have?
So it's a 3.
Exactly. And that's why when we add these two numbers together, we retain 3 decimal places.
Okay.
Yep.
Thank you.
So the answer in Canvas may have been calculated using a slightly different set of atomic masses. Depending on the amount of precision, you may notice a little bit of drift in the answers, but you'll still get credit if your setup is correct and you've entered everything in one line in your calculator, then it should be within the error tolerances. If not, I'll adjust the tolerances for the Canvas quiz to account for a small amount of drift after you round these numbers.
Hey, Professor, I got a different number on your 20% calculation.
Yes.
I got 2.00258.
Oh, yeah. Sorry about that. There we go. Perfect.
Okay, cool.
Let me just re-enter this into the calculator really quickly. $2.00258. Yep. Perfect. And we'd retain 4 sig figs, which would result in 3 decimal places.
So like you said, you don't want us rounding like on this one, you'd rather have us use that bar notation?
Yes.
Okay.
Or what you'd do is you'd enter this into your calculator as one line, carrying it through all the steps of the calculations in one line.
Okay, yeah, I see what you're saying. Okay.
Mm-hmm. And that's the best way to minimize rounding error in these problems.
But then we'd have to separately just like count sig figs on top and then do the addition with the decimal. Okay.
Yep, exactly right. Any other questions I can address on this problem?
Not for this problem specifically, but I was just wondering, like, since all of these are due by the end of the week, and we're keeping up with it, is there a certain way in Canvas we can see like all of them together just to make sure we didn't like miss any?
Yes, if you go to the grades tab, it will show all of these problem solving sessions, as well as whether you've completed them. If a score is present, you have completed them.
Okay, and then I guess more my question is just so that way Well, I guess all the ones that are listed here should be done by the end of the week then, yes?
Yes, yes. And
Okay.
any ones that we haven't done yet or that may carry over into next week, you won't be responsible for until that next week.
Okay, cool. So
Yeah.
basically they should just be done here. If they're listed, we've probably done them.
Yeah, exactly.
Okay.
Mm-hmm. So let's keep going now and let's tackle really one of the central ideas that I like to introduce in general chemistry is this idea that algebra is a very wonderful tool for saving you time in having to do calculations in a repetitive manner. So what do I mean by that? So let's suppose we have an element with two isotopes. We can actually determine the percent abundance of each isotope given the mass of each isotope and the average atomic mass. And we're going to show this algebraically rather than working through each solution on a case-by-case basis. We can figure out and create a general equation. So I'll show this derivation now. So let's talk about our variables. So I'm going to call M1 is going to be the mass of isotope 1. Okay, and %1 will be the percent abundance of isotope 1. M2 is going to be the mass of isotope 2. And %2 will be the percent abundance of isotope 2. Okay, so from here, we know first and foremost that the average atomic mass that I'm going to call M average is equal to the mass of isotope 1 times the percentage of isotope 1 over 100% plus the mass of isotope 2 times the percentage of isotope 2 over 100%. Sure. All's well and good. This is something that we've used actually in the previous example. What we also know is that if I take the percentage of isotope 1 and I add it to the percent abundance of isotope 2, if I add up both of my percent abundances for all of the isotopes of an element, what should these percentages add to? If I only have two isotopes and I add their percent abundances together, what should these percentages add to?
100.
100%, exactly. So then we can now rearrange this equation. So we have two equations and two unknowns. So algebraically, we can solve them as the system of equations. So the percentage of isotope 1 is equal to 100% minus the percentage of isotope 2. So what we're going to do next is we're going to plug in this expression into our first equation. So that gives us the average atomic mass is equal to the mass 1 times 100% minus the percentage of isotope 2 over 100% plus the mass of isotope 2 times the percentage of isotope 2 over 100%. Now we're going to group together all of our terms with the percentage of isotope 2, and that in turn gives us the average atomic mass times 100% is equal to the mass 1 times 100% minus the mass of isotope 1 times the percentage of isotope 2 plus the mass of isotope 2 times the percentage of isotope 2. Now we have two terms with the same variable next to them. So we're going to preemptively move this term to the left. So we get the average atomic mass times 100% minus 100% times the mass of isotope 1 is equal to the mass 2 plus the mass 1 times the percentage of isotope 2. Then all we have to do now All we have to do now in our system of equations is solve for the percentage of isotope 2 by moving this mass term to the left. So that gives us the average atomic mass minus the mass of isotope 1 times 100% over the mass of isotope 2 plus, oops, that should not be a plus, that should be a minus. Mass of isotope 2 minus the mass of isotope 1. So this is a general equation that works for any element with 2 and only 2 unique isotopes. And this allows us to, given the mass of our isotope and the average atomic mass, it allows us to calculate the percentage of each isotope using the following 2 equations. Does this make sense to everyone so far? Any questions on this derivation? Once we have the setup based on chemistry, the rest is just the application of algebra. But the real power of this is we don't have to consider things on a case-by-case basis. If it's a 2-isotope system, we have a general method of solving any of those problems.
Hey, Professor, so this is when like you're looking for either of the percentages.
Mm-hmm.
So like, for example, you're only giving one and then they want you to find the other one?
So this is, if we're given the masses of each of our isotopes, we can calculate the percentages of both isotopes. Mm-hmm.
Okay, I guess I got to see an example and then.
Oh, sure, definitely. We're going to show the application of this in this next example here. And this will really help showcase how it works. So, oops, one moment. Let me set to the example. Give it 1 second. Okay, so let's take a look. We're given the following information in this problem. Carbon has an average atomic mass of 12.011. Carbon has 2 major isotopes, carbon 13 and carbon 12. We're asked to calculate the percent abundance of each isotope. So we know that the percentage of carbon 12 plus the percentage of carbon 13 is equal to 100%. We're going to arbitrarily designate the percent 1 as the percentage of carbon 13. The mass 1 as a result is the mass of carbon 13, which is 13.003 AMU. The percentage 2 is going to be the percentage of carbon 12, and the mass of isotope 2 will be 12 AMU, just reading from the problem. The average atomic mass is going to be equal to 12.011 AMU. You can get this from the problem or the periodic table. So note, I don't always have to give you the average atomic mass. You have the tools to look it up. Okay, so now that we have all of our variables set up, we're going to use this equation that we derived previously. So the percentage of isotope 1, which is the percentage of carbon 13, is equal to 100% times the atomic mass, which is 12.011 AMU, minus the mass of isotope 2, which is 12 AMU. You can write AMU with a U symbol. That's the symbol for atomic mass units. Okay, and then we divide by the mass of isotope 1, which in this case is 13.003 AMU, minus the mass of isotope 2, which is 12 AMU. And if we punch this into our calculator, we get the percentage of carbon 13 to be 12.011 minus 12 divided by 13.003 12.011 minus 12.011 minus. These are a little bit annoying to enter in your calculator. Just make sure you're careful with it when you're entering your values into your calculator. So in this top portion, we'd have 0.011 AMU. On this bottom portion, we'd have 1.003 AMU. Note the mass of the carbon-12 nucleus is an exact number. Okay, so now that we have our two numbers in place, we notice this top number has 2 sig figs. So after we complete our division operation, the percentage of carbon-13 is equal to 0.011 over 1.003 times 100%, and that gives us 1.096%, which we are forced to round to 2 sig figs, which gives us 1.1%. The percentage of isotope 2 is equal to 100 minus the percentage of isotope 1. And remember, isotope 2 is the percentage of carbon-12. We get 100 minus 1.0967, which in turn, this has 1 decimal place. We get out the answer of 98.903, which we round to 1 decimal place, which is 98.9%. Notice as a check, if we add both of our percentages together, we get 100%. So does this make sense how the equation we derived can be used to, given the isotope mass and average atomic mass, it can be used to calculate the percent abundance of each isotope? Does this make sense to everyone so far?
Can you explain the part after the 1.1%?
Yes. The total, if you add both of the percent abundances together, you will get 100%. So then we can solve for the percentage of carbon-12 by taking 100 minus the percentage of carbon-13.
Okay, and right now for 1.1, that is carbon-13?
Yes.
Carbon,
and
okay.
The percentage of carbon-12 is 98.9. The 2 sig figs came from the fact that after our subtraction, we have a number with 2 functional decimal places. So as a result, our answer needs to be rounded to 2 sig figs after we divide. So this number of 0.011 has 2 sig figs. So when you divide, your answer must have 2 sig figs. Does that make sense? That's why I sometimes write out the intermediate numbers that you get after the first step in a calculation, just so that way we can see how many sig figs we need to report.
And we're always getting the least decimal place?
So for subtraction, it's the least number of decimal places. For division, it's the least number of total sig figs. And because we have 2 sig figs and we're dividing, our answer needs to have 2 sig figs. Does that make sense?
Not really, but I'm gonna have to just study that more. It's fine, thank you.
In general, addition and subtraction, you take the least number of decimal places, and multiplication and division, you take the least number of sig figs. I'm talking about sig figs in this context, just because it's always important to be conscientious about sig figs. But if you're able to do these calculations and your sig figs are a little bit off, you'll still get the majority of the points for a correct calculation. So really focus on understanding how the calculations function, and then as a side, think about how the sig figs function. Does that make sense?
Yeah, it does. Thank you.
For that second line, what does it say? Times 100% times mass average equals 12?
Oh no, just times 100%. I just made a table of all my variables, just so that way I know what I'm entering. So just putting this on the side. This is just my table that I like to read off of from the problem. So that way I know what I'm plugging in and what I'm putting where in each of my equations.
Okay.
It's just an organizational tool that I like to use to keep me from entering the wrong things in my equation and creating an incorrect answer.
Could you write that first part that's in brackets with variables and explain that again?
This first part right here, I can annotate it for sure. Okay, so let's annotate it. So this first part is the average atomic mass. The second part is the mass of isotope 2. Here is the mass of isotope 1, and here is the mass of isotope 2. So in effect, what we're doing is we're subtracting the mass, the average atomic mass, by the mass of isotope 2, and then dividing by the difference between the mass of isotope 1 minus the mass of isotope 2.
Will we be having to memorize all of these formulas, or are they given to us on the quizzes?
The reason why I showed the derivation is because you are responsible for knowing the formula for average atomic mass. And from that formula, you can manipulate it to get this equation. Or if you prefer, you can memorize this equation. Although it's important to understand how this equation was obtained so you can understand how to modify it to deal with variations on this problem. Does that make sense?
Yeah, thank you.
Did that address your question about how each of the variables are being plugged into this equation?
Yeah, that looks pretty good. Thank you.
Okay, perfect. So let's now try an example on our own. This is pretty similar to what you may see on a quiz or exam. So let's try to tackle this problem, except this equation would be absent. I'm getting people used to using this equation and this thought process. But you want to understand how we created this equation. So that way on an exam, it's easier to recall. So let's take about 5 minutes to work through this problem. I'd like you just to calculate the percent abundance of each isotope, given the mass of each isotope for lithium and the average atomic mass. And then we'll discuss in about 5 minutes. I'm already seeing some reasonable responses in the chat, but let's take a few more minutes and let's try to report the percent abundance of each of our isotopes of lithium. And if there are any questions when solving this problem, don't be shy to message me using the Zoom chat feature.
Is mass 1 and mass 2 considered those two isotopes?
Yes, and you can pick which isotope you designate as isotope 1 and isotope 2.
So since we're finding the percent for each, are we basically switching it when we go for the second one?
Yes, or you can use the fact that the 2% abundances will add up to 100%. Yep.
Okay.
Perfect. So we'll spend about another 3.5 minutes on this. I'd like to get a few more responses via the Canvas quiz app or in the chat, and then we'll discuss momentarily. So in this problem, I'm asking for the percent abundance of each individual isotope. Yes, both of the percent abundances will add to 100%. But when you submit your answer in the chat, if you could indicate which isotope you've calculated the percent abundance for, it would help me provide feedback. We'll spend another minute and a half on this problem. I want to get a few more responses via Canvas or in the chat, and then we'll discuss momentarily. Any questions working through this problem? We'll discuss in about 1 other minute. I want to see a few more responses just to check to see how everyone's doing on these calculations. This is very similar to the type of calculation that you'd be expected to do on an exam or quiz. And these also show up a fair bit in the online homework as well. So I'm already seeing some reasonable responses in the chat. So let's begin to discuss this problem. So first and foremost, I'm going to arbitrarily designate isotope 1 to be lithium 7. So the mass of lithium 7 is 7.016. The mass of isotope 2 then is the mass of lithium 6, which is 6.015 AMU. The average atomic mass is equal to 6.938 AMU. Now we have all the information we need to solve for the percentage of isotope 1, which is the percent abundance of lithium 7. So we take 100% times the average atomic mass, which is 6.938, minus the mass of isotope 2. Divided by the mass of isotope 1 minus the mass of isotope 2. Oops, one moment, sorry. We take the atomic mass minus the mass of isotope 2, which is 6.015 AMU. So this is the average atomic mass, this is the mass of isotope 2, this is the mass of isotope 1, this is the mass of isotope 2. So, calculating the percentage of lithium 7, we get 100% times, and let's see what this looks like after our first step in the calculator. We're dealing with subtraction, so we have 0.923 AMU over 1.001 AMU. So when we perform a division operation, division cares about Sig Figs. So since our top number has 3 Sig Figs, our answer needs to have 3 Sig Figs. So then we get out as a raw answer 92.207, and we round it to 3 Sig Figs. We round down, and that gives us 92.2%. The percentage of lithium 6 is equal to 100% minus the percentage of lithium 7, which is equal to 100% minus 92.2, which gives us 7.8%. Any questions on this example? Does this example make sense to everyone so far?
When finding the percentage for lithium 6, it's fine to just use the 92.2, right? We don't have to use the 92.207.
Ideally, you'd want to use the full number, but in this case, it doesn't make a difference.
Okay.
Mm-hmm.
All right, cool.
Any other questions? Yes, so for finding a second isotope, you can just subtract. You can also calculate it from scratch if you want to, though that takes a little bit more time. And if you did the first calculation accurately, you wouldn't have to do the second. You wouldn't have to use this equation again. Does that make sense? Perfect. So let's talk about an additional case, and let's just sort of show how we can adjust our logic if we have to deal with a more complicated equation. So let's ask ourselves the question, how would we determine the percent abundance of each isotope if an element has 3 isotopes? Well, we can't just use the same equation. For 3 isotope systems, you need 1% abundance to be given. So our atomic mass expression looks like this, where we have the percentage of each isotope times the mass. Sometimes there's drift because depending on how accurate and how many sig figs are provided for the mass and the percentage and what exact source is used for the mass and percentage, there may be a small amount of drift in the answers. So especially for the isotope abundance questions, it's important to use the exact values given. Probably in Canvas, when I calculated it, I was using a different reference book. And as a result, the values were a little bit different for the percent abundance. As long as you're within a general margin of error, you'll receive credit if your setup is correct. Does that make sense?
Yeah, are we supposed to be showing the work for the quizzes? Because I've been just putting the answer.
Yeah, those are just the spot checks, the problem solving sets that we do during class are just scored based on completion.
Okay.
For quizzes, you can submit a sheet with your work. It's not required. If I see that your answer is off by 0.1 and there's no common error that would result in that, I'll just assume it's a small rounding error and I wouldn't take off points for it.
Mm-hmm.
It's mainly just for some problems, especially in the online homework. The online homework can get a little finicky as to it wants the exact answer in a really small range. So you want to make sure you're using the values given because even small changes in the given percent abundance or given mass can massively change your final answer.
Mm-hmm.
Does that make sense?
Yes, thank you.
So let's talk about this next example where if we have 3 isotopes, suddenly we have 3 terms in our equation. So let's suppose if we're given a percent abundance. So if we were given a percent abundance, let's suppose we're given the percent abundance of isotope 3. We can now rearrange this equation and move our percentage of isotope 3 term to the left-hand side. Now we're going to call this chunk of constants on the left the adjusted mass M. Okay, so just like before, the percentage of all of our isotopes will add to 100%. So then we can solve for the percentage of isotope 1 and write it in terms of the other two isotopes. Now, if we substitute this expression back into our average atomic mass equation, we get the following simplified equation. M, which is our adjusted atomic mass, is equal to 100% minus the percentage of isotope 3 minus the percentage of isotope 2 over 100 times the mass of isotope 1 plus the percentage of isotope 2 times the mass of isotope 2. Now, I'm not necessarily expecting you to memorize this derivation, not at all. I just want you to understand that the theme for this derivation is exactly the same as before. The only thing new is the algebra gets a little bit more tricky. That's why I've just typed it out instead of written it out, just because it really is, the only thing that's changed really is just the algebra required. If we solve for the percentage of isotope 2, we end up with the following expression. So the percentage of isotope 2 is equal to the adjusted mass times 100 minus the mass of isotope 1 times 100 plus the mass of isotope 1 times the percentage of isotope 1 over 100%. Oh, sorry, over the mass of isotope 2 times the mass of isotope 1. So this is a modified equation that you'd use for a 3-isotope system. So in many cases, it may be easier to solve these 3-isotope problems stepwise, but there is always a way to generate a general solution. Not a ton of these problems, but definitely at least a few on, at least one at minimum on the exam. So now that we have a framework and a general solution for a 3-isotope system, let's talk a little bit about how we can apply this. So let's suppose we're dealing with magnesium, which has 3 unique isotopes. We know the average atomic mass of magnesium is 24.307, and we know the mass of our 3 isotopes, magnesium 24, 25, and 26. We're also given the percent abundance of magnesium 26 as 11.01. Okay, so we know that our average atomic mass is equal to 24.307. We know the mass of isotope 1 is 23.9805. The mass of isotope 2 is 24.9858. Whoops, one moment. Okay, we are also given that the mass of isotope 3 is 25.9825, and we're given the percentage of isotope 3 to be 11.01%. We now have all the tools that we need to solve for the percentage of each isotope. So first, we're going to calculate the adjusted mass, which is the average atomic mass, which is 24.307 AMU, minus the percentage of isotope 3, which is 11.01% over 100, times the mass of isotope 3, which is 25.9825 AMU. So this gives us an adjusted mass. Let's punch that into our calculator. This gives us an adjusted mass of 2.86067, and we'd only retain, in this case, let's just check really quickly, 25.9825 times 11.01 over 100. This answer is 2.8606. It has 4 sig figs, so we'd only care about 3 decimal places. Perfect. Okay, so we have the adjusted mass checked off. Now we're going to plug that into our equation for the percentage of isotope 2. So we take our adjusted mass times 100% minus the mass of isotope 1 times 100% plus the mass of isotope 1 times the percentage of isotope 3 divided by the mass of isotope 2, which is 24.9858, minus the mass of isotope 1, which is 23.98. Should be 50. Okay, perfect. So let's just put our labels on each of these numbers that we have obtained so far. Let's just put a label so we can recognize what's going on. So we have our adjusted mass. We have the percentage, we have the mass of isotope 1. We have the mass of isotope 1, the percentage of isotope 3, the mass of isotope 2, and the mass of isotope 1. Just mapping on our variables. Just like in above, here, we add the average atomic mass and the percentage of isotope 3 and the mass of isotope 3. So now let's punch this into our calculator. Let's punch this into our calculator. So we have 2.86067 times 100 minus 23.9850 times 100 plus 23.9850 times 11.01. Let's just check our calculations really quickly just to make sure. So we have, let's check this first calculation really quickly, just to double check that there wasn't a calculator error in this first step. So we have 11.01 over 100 times 25.9825 So after the first step, we get negative 20, oops. We get 21.4463. There we go. And this is our adjusted mass. So let's punch that into our calculator now. It's better to enter this all in as a one-line calculation because when you carry digits through, there's often a high chance for you to perform a calculator error. And if you've done everything correctly in the first top line of your calculation, you'll get the percentage of isotope 2 is equal to 10.20485, where we only care about 3 decimal places, and then divided by 24.985 AMU. Oh, sorry, 9858 AMU minus 23.9850 AMU. And if we punch that in our calculator, we end up with 10.20485 over 1.0008. And if we punch that into our calculator, we in turn get a percent abundance of isotope 2 of 10.19669 that we round to 10.197 following Sig Fig rules. Let's just check. Yep. 3. One correction, this number here has 2 decimal places. So we'd only care about 2 decimal places, which would mean our answer would be rounded to 4 sig figs, which would be 10.20%. Don't worry a ton about the sig fig rules for these super complicated multi-step calculations. Just understand the theory between how to apply this equation, how to execute on these calculations, and how to report your final result. Now, given that the percentage of isotope 2 in this case is the percentage of magnesium 25, and we know the percentage of magnesium 26 already is 11.01%, we can solve and we can use one more equation. Given that all of our percent abundances add to 100, we can solve for the percentage of magnesium 24 by taking 100 minus the percentage of magnesium 25 minus the percentage of magnesium 26. So that in turn gives us 78.79%. So even though it's a little more finicky to enter into your calculator, the theory behind this process is exactly identical to our 2 isotope system. Are there any questions on these examples? It's really important just to check your work when going through the calculations to make sure you didn't make a calculator error. And otherwise your percentages should all add up to 100, and they should obviously be between 0 and 100 and be positive numbers. Any questions on these calculations?
So that M21.4463.
Yes.
How do we get that number? Because previously didn't we have 2.8606?
So I went through and I redid the calculation. The way that you calculate M is by taking your average atomic mass minus the percentage of isotope 3 over 100 times the mass of isotope 3. And then when we punch that into our calculator, we get 21.446. The 2.86 is the result from this first step. Does that make sense?
Yeah.
Perfect. Any other questions on this example?
Yeah.
Oh, go ahead.
No, go for it. You're good.
So we're not rounding until the end?
Yes, that's correct.
Okay. Because I see that you're still putting the bar, like for example, 21.4463, but then you continue using the entire number on the next step.
Exactly.
Okay. Yep. Okay.
It's especially important for these kinds of isotope problems that you don't round until the end, or you'll introduce rounding error.
Okay.
Sometimes why the numbers are a little different in Canvas. Any other questions?
Yeah, I was still confused on the 10.204, how you use 4 sig figs, but how it has subtraction and there's like more decimal places.
It's because from this number here, right here, from 11.01 times 23.98, so 23.9850 times 11.01, that in turn gives us 264.07, in which case we only retain 4 sig figs, and as a result, when we add these numbers together, we'd only be able to retain 1 decimal place. Actually, that's a good point. And as a result, each of our answers, we can only report up to 3 sig figs. Here we go. So the bar indicates the last reported significant digit.
So because that one has the percentage, which is 4 significant figures, you technically go based off that one since the other ones are just 100%.
Yes, and 100% is an exact number.
Okay, and then like you said, you go based off the 1 decimal point for the rest of the subtraction and addition?
Exactly.
Okay, cool. That makes sense. Okay, thank you.
Don't worry a ton about the sig figs. They're important for sure, but I'm mainly looking in these sorts of problems that you can do the calculations. If the calculations are done perfectly and you have a small sig fig error, it's not a big deal. It's maybe 1/4 of a point.
Okay, and like you said, if you punch it into the calculator, it should give you pretty much the number.
Yes,
like,
no rounding errors.
Okay, cool.
The reason why I show all these intermediate steps is so that way you can see where the sig figs come from.
Okay, cool, cool, thank you.
So just to test that everyone's comfortable with this idea, let's give everyone about 6 to 7 minutes and let's try to tackle an exactly identical problem to the one we've just shown in Canvas Quiz 2.12-2. This time, I give you each of the isotopes of silicon and the average atomic mass, and I'd like you to calculate the percent abundance of each isotope of silicon. And don't be shy to submit your response via the chat feature or using the Canvas quiz feature.
If we would we also be able to solve for each isotope basically, if we want to do it like the long version, just like each one. Like in, I guess I didn't explain that right. I'll see if I can do it right now.
You can just make sure that you're retaining all of your digits when you carry through the calculations.
Oh yes, okay.
Because the main issue with the stepwise method is that oftentimes rounding errors get introduced, and then you end up with percentages that can be substantially off because the numbers are so small.
Okay.
Mm-hmm. But either method that you're comfortable with is fine. I'm already seeing some reasonable responses in the chat. Let's spend another 6 minutes on this problem, and I'll be checking Canvas just to see responses via Canvas, and I'll be checking the chat. So if you'd like to share your response, really don't be shy. It helps me get a sense of how far everyone's along in the problem and allows me to give the appropriate amount of time for each question during these problem-solving sessions.
When you do the percent abundance for M, when you're trying to find the percent isotope, do you leave it as a percent or do you turn it into a decimal?
Either is acceptable. Both would work.
Okay.
There's no so sorry. When you mean, so for the percent abundance in the equations that I provided, you're going to enter the percentage exactly as the number given. The way that the equations are set up, the equation will automatically convert the percentages into decimals when needed. So for the percent abundance, you'd enter this number exactly as written into the equation. Does that make sense?
Yes.
Perfect. And if you have any additional questions, don't be shy to unmute and ask, or ask them in the chat. I know these problems are a little more involved, but it's setting the stage for not necessarily the types of problems, but the level of difficulty of some of the problems that we'll be tackling in later chapters as well.
I just have a question about Sig Figs. So
Sure.
when you're doing the small m, when you're doing the percent isotope of the third one over 100 times the mass, when you do the 100 times the mass, you take the least amount of Sig Figs, right?
Yes, but you consider 100 exact. And just to help you a little bit, you can, in terms of order of operations, you take the percentage of isotope 3, divide it by 100, and then multiply it by the mass.
Oh, okay. So then it's 3.092 divided by 100 and then times the mass.
Yep. Yeah.
Okay. Thank you.
Mm-hmm. Let's try to get a few more responses via Canvas or in the chat, and we'll discuss in about 3 to 4 minutes. I want to see some responses just so that way I can get a sense of how everyone's doing on these calculations. No, it's no problem at all. No problem. There's no rush. I'm more than willing to give everyone more time. It's better to be accurate, especially when it's the first time you're working on these problems. Everyone will get quite faster with these the more that you practice on the online homework and in the problem-solving sets.
So do we consider 100 as 3 Sig Figs? Or
consider it like an exact number and don't worry about its sig figs in your calculations.
Okay.
Think of 100 like having unlimited sig figs. So it's
Okay.
infinitely precise.
So then we would use the percentage sig fig instead
Yeah.
of the 100.
Yeah, exactly. And we'll discuss in about another 3 minutes. Let's try to get a few more responses via Canvas, but don't worry if you need more time. I'm more than willing to give everyone more time so that way we can have everyone submit their responses and get feedback either through Canvas or from me from me via Canvas or from me via the chat when I see it in the chat.
So after you find M,
Yep.
when you input it into the equation, do you put the whole number or do we just put it to however many sig figs?
The whole number.
Okay.
Mm-hmm.
But just keep in mind what the sig figs are.
Yep, exactly right.
And then what's considered mass 1 and mass 2? So mass 2 is the bigger isotope?
You can pick whichever one you prefer. How you label your variables is completely up to you. So you can really pick either of them as long as you're consistent. Does that make sense?
Yeah.
Perfect. Let's try to get a few more responses either in the chat or via Canvas before we discuss this problem.
Excuse me?
Yes. Mm-hmm.
What would be the best way to calculate it? Like, I'm just using my calculator on my phone, but would it be better to do a scientific calculator, or when I do
Yes.
mass times 100, do I do it in parentheses or like separately?
It would be highly recommended to do these calculations and most of the calculations in this class on a scientific calculator. If you are waiting for your scientific calculator to arrive, I would do each calculation stepwise and write down the full number for each step, just so that way you don't lose place of sig figs. Does that make sense?
Yeah. Okay.
Mm-hmm.
So the m times 100 would be its own calculation, and then I would do minus mass 1 times 100?
Yep, exactly.
Okay.
Mm-hmm. let's try to get a few more responses, just that way we have more than the majority of the class receiving feedback on these types of problems. Any questions while you're working through this problem? We'll discuss in a minute if we have a few more students respond. Just want to give everyone enough time to work through this problem and get a sense of how solving these problems works. Okay, we have a nice pool of responses to discuss, so let's talk about this problem. So first and foremost, let's make a table of values that we know. So the mass of isotope 1, which we'll call silicon 28, is 27.9769. The mass of isotope 2 is 28.9765. The mass of isotope 3 is 29.9737. And the percentage of isotope 3 is 3.092%. We're next going to calculate our adjusted mass. Whoops, we need one more piece of data, which is the average atomic mass of 28.086 AMU. So then, the adjusted mass is the average atomic mass minus the percentage of isotope 3, which is 3.092%, times the mass of isotope 3, which is 29.9737 AMU over 100. And that in turn gives us
Wait, is that all over 100 or is it just the 3.092?
just the part on the right. Just the part on the right.
So it's 3.092 times 29.9737 over 100.
Yep, exactly right. And after subtraction, we get 27.1592 AMU. Now we'll plug everything into our overall equation for the percentage of isotope 2. So we'll plug in our adjusted mass.
Why is the 2 have the bar? I thought it was 5 Sig Figs.
Yep, sorry about that. Sometimes the drawing program experiences a delay and it ends up putting a mark in the wrong location. Okay, so times 100. Oops. There we go. Minus the mass of isotope 1, which is 27.9769 AMU times 100, plus the mass of isotope 1, which is 27.9769 AMU times the percentage of isotope 3, which is 3.092%. This is all divided by the mass of isotope 2, which is 28.9765 AMU, minus the mass of isotope 1, which is 27.9769 AMU. So now all we have to do is punch this into our calculator, assuming our calculator is reliable. And for most scientific calculators, this should be no problem whatsoever. So let's deal with the top portion first.
My calculation had some extra digits, so for my 27.1592, I also had 3 more digits after it.
Yep, you'd carry through the rest as well. I just don't have enough space to write them all out, but I am storing them in my calculator, and I'll write out the full output in the next line.
Oh, okay.
Mm-hmm.
Which Canvas quiz is this? I'm sorry, I was looking at it off Zoom.
Whoops, one moment. 2.12-2.
Thank you.
Okay, so for our percentage of isotope 2 in our first line, we have 7.3457. However, if we look at the result from this calculation on the right, we have 3.092 times 27.9769. That in turn gives us 86.50 for 4 sig figs, 2 decimal places. So we can only report up to 2 decimal places. For this bottom calculation, we have 28.9765 minus 27.9769. And that gives us 0.9996 AMU. So at the end of this, we're only allowed to report 3 sig figs. And that in turn gives us a percentage of isotope 2 of 4.74%. Okay.
Why did you multiply the third isotope by the 3.092% and not 100?
Oh, because in our equation, all the way up here, whoops, one moment. Notice how the first 2 masses are multiplied by 100, while the mass of isotope 1 is multiplied by the percentage of isotope 3. This is just
so then we use whatever the given percentage is.
Yep,
and
exactly.
then to find the rest of it.
Yep, exactly.
Okay.
Did the 3 sig figs come from 100?
The 3 sig figs in this case, let me show that here. So the reason why I showed the result from this multiplication step, let me show that one moment. All right, there's a small delay when it's streaming, so let me get it lined up and scrolled over before I discuss this. Okay, so I showed the result of the calculation on the right-hand side because it shows that our answer has 2 decimal places. After all of our addition and subtraction operations, this answer will have 2 decimal places. Now, following that idea, as a result, because this number has 2 decimal places, it functionally has 3 sig figs. And as a result, our answer must then have 3 sig figs. Does that make sense?
I'm slightly confused. Why did you put 27.9769 twice?
Because in our equation up here, the mass of isotope 1 appears twice in this equation.
Oh, okay.
Mm-hmm. Does that make sense?
Yeah, it does.
Perfect. So now that we have the percentage of isotope 2, which in this case, this percentage corresponds to the percentage of magnesium 29. We also know that the percentage of magnesium 30 is 3.092%. So we can solve for the percentage of magnesium 28 by taking 100% minus the percentage of magnesium 29 minus the percentage of magnesium 30. And so to cap out this problem, we get 100 minus 4.74 minus 3.092, which gives us a percentage of 92.168 that we in turn round to 2 decimal places. So we get 92.17%. For these problems, there are a few of these types of problems in some additional optional homework, and I can certainly make and post a few more of these if you'd like to attempt them again as well.
I'm a little confused on something.
Yes.
The first equation that we did, the first formula,
Mm-hmm.
what was that for? So what is that for? It's mass?
This is known as the adjusted mass, and it's just breaking up the calculations into pieces. So that way this equation where we enter all of our numbers into doesn't get massive. So the problems that you see in mastering chemistry will probably only go up to 2 isotope systems. I'm just showing 3 isotope systems because they may appear in the homework and may appear in certain common created exams, but this is about as difficult as it's gonna get.
So we didn't use that, correct? Like we didn't actually use the 27.15.
Oh no, we did. So this mass is inputted in right here.
Oh, okay.
Does that make sense?
Yeah, and that's part I had put 28.086.
And
I had put atomic mass.
Yeah. Mm-hmm. Does that make a little bit more sense now?
Yeah, and did we use the atomic mass for anything?
Yes, the atomic mass gets inputted right here.
Okay, got it.
Perfect.
Thank
So essentially for these types of problems, we only need 2 masses and the percent abundance of one of the masses.
Yes, exactly. Yeah, I wouldn't worry too much about these 3 isotope problems. I'm covering them for completeness and just so that way there's an option for me to ask them. But you should know 100% how to do a 2 isotope problem. Those will show up a fair amount in the homework, and you'll definitely see at least one of those on a quiz.
So it seems like 3 isotope problems. I know we shouldn't stress too much over it, but so they have like a different type of equation and setup versus the 2 isotopes, correct?
It's a different equation, but their overall setup and the process for solving them is identical.
Okay, because I realized like halfway through solving that it was easier than I assumed because I didn't realize they gave us the percent of the 3rd isotope.
Oh yeah, they have to, otherwise you won't be able to solve this equation.
Yeah, I was trying to do it without that and it was very confusing.
Does that make sense now?
Yes, it makes a lot more sense.
Okay.
So
yes, go ahead.
for the quiz question, it's asking for 28. So that's the first isotope? The first one?
Let's see. Oh, whoops, sorry. This is silicon. So then for silicon 28, that is the first isotope, yes. So this, let me replace, I'm stuck on magnesium because that was the one that we did in the previous problem, but yes, the percent abundance of silicon 28 is the first isotope. Yeah.
Okay,
Mhm.
thank you.
So for the exams, I was wondering, is it going to be strictly on what you lecture on? Is there anything that we should be reading from the book?
So if it's covered in the book or mastering chemistry, it can be fair game, but I will generally focus on the topics that I lecture on and that we do problems on. So the majority of the types of questions that you'll see and the content that you'll see for exams will closely match the lectures that you are participating in, as well as any supplemental homework I provide. And if it's easier, you can memorize the formula, or you can understand how these equations are created, and that way you can just derive them when you're working on the exam, whatever you prefer. Did that make sense to everyone? Perfect. So now let's take a bit of an intellectual breather, as we're going to cover a less calculation heavy topic for sure. And just give me 1 second to reset OneNote, just so that way we have less delay. Okay. And we're going to deal with some relatively straightforward chemical and physical laws at this point. And these are really the cornerstone of empirical chemistry and the development of chemical laws. So let's get the chat all up and running. Okay, so first and foremost, the law of conservation of mass. Let's walk through the principles behind the law of conservation of mass. So atoms cannot be created or destroyed in chemical reactions. So for example, if I try to react hydrogen with chlorine to generate hydrochloric acid, the number of atoms of each element before and after a reaction does not change. So if we go from, we take hydrogen gas and chlorine gas and we react them to make 2 molecules of HCl, we have 2 hydrogen atoms and 2 chlorine atoms on the left. We have 2 hydrogen atoms and 2 chlorine atoms on the right. The number of atoms before and after, the number of atoms of each element before and after a reaction does not change. Further, the total number of subatomic particles does not change. So if we think of for example, so if we're thinking, for example, of a hydrogen atom, this hydrogen atom can be thought of as a bundle of a proton and an electron. So if atoms are unchanged, the number of particles does not change. And this will come up when we start to discuss redox reactions, or reactions that involve the transfer of electrons. Now, we clearly know and we've seen that atoms have mass and subatomic particles have mass. Now, since atoms have mass and the number of atoms of each element doesn't change, the total mass before and after a reaction doesn't change. So for example, if we take hydrogen and we react it with oxygen to generate hydrogen peroxide. If we start with 2 grams of hydrogen and 32 grams of oxygen, how many grams of hydrogen peroxide will we make? How many grams of hydrogen peroxide will we end up with? If we start with 34 grams, how many grams will we end with? 34 grams. The mass before and after a reaction doesn't change, but the chemical identity of that mass does change. Okay, so let's look at some depictions for conservation of mass. So let's suppose we mix sodium and chlorine to make sodium chloride. If we start with 7.7 grams of sodium and 11.9 grams of chlorine, so 19.6 grams total, we will end up with 19.6 grams of sodium chloride, assuming a perfectly quantitative reaction. On a micro scale, we can even look at this process from a micro scale if we look at water and oxygen reacting. In this case, we have 4 AMUs of hydrogen. We have 32 AMUs of oxygen. So how many AMUs of water will we make? What mass of water will we get out? 34. Oh, sorry, not 34. 32 plus 4 would give us 36. Yep. So as we can see, mass is conserved at a macro scale with bulk reactions of material and on the particulate or micro scale. Even at the single molecule scale, mass is conserved. Okay, so let's look at how we can use the law of conservation of mass to solve chemical problems. Oops. Here we go. So let's look at a guided example now into how we can apply the law of conservation of mass. So a reaction of 22 grams of sodium with oxygen gas generated 30 grams of sodium oxide. Okay, so it's asking what mass of oxygen reacted with 22 grams of sodium metal to generate 30 grams of sodium oxide. So we know that the mass of sodium plus the mass of oxygen must equal the mass of sodium oxide. The mass of our reactants must equal the total mass of our products. So then, solving for the mass of oxygen, we take the mass of sodium oxide minus the mass of sodium. So then the mass of oxygen is equal to 30.0 grams minus 22.0 grams, which gives us 8.0 grams of oxygen. Does this logic make sense to everyone? Does this logic make sense to everyone? Yes, it's relatively straightforward, yes? Mm-hmm. So let's try to test our understanding of this concept by tackling the following problem. So a reaction of 63.5 grams of sodium metal with chlorine gas generated 134.4. Oh, sorry. Let me just make an adjustment. Should be copper metal. Reaction of 63.5 grams of copper metal with chlorine gas generated 134.4 grams of copper chloride. And we're asked in this problem to figure out what mass of chlorine reacted with 63.5 grams of copper to generate 134.4 grams of copper 2 chloride. Yes, the Sig Figs do matter, and we follow the Sig Fig rules for addition and subtraction. So let's spend about 2 minutes working on this problem. And don't be shy to submit your responses via the Canvas quiz feature or the chat. And don't be shy to message me with any questions you have about this problem solving session 2.14. We're already seeing some reasonable responses in the chat. Let's get a few more in the chat or via Canvas before we discuss this question. So I'm seeing a lot of reasonable responses. So let's discuss this question. So we know that the mass of chlorine is equal to the mass of copper chloride minus the mass of copper. So we take 134.4 grams minus 63.5 grams, and that in turn gives us 70.9 grams of chlorine. Yep, not too bad. Any questions on this example? Any questions on this example? If not, let's keep going then. Let's talk about one of the two major set of Dalton's laws, which is Dalton's law of definite proportions. And this essentially states that compounds have a definite fixed number of atoms of each element. Each compound has a specific fixed whole number ratio of atoms that make up that compound. All samples of the same compound have the same number of atoms of each element in their formula and structure. So for example, carbon dioxide, CO2, has one carbon atom and two oxygen atoms. This is true for all samples of CO2. Now, unique compounds have a unique number of atoms of each element. So for example, carbon monoxide has one carbon atom and one oxygen atom, while carbonate anion has one carbon and three oxygen atoms. So a unique compound will have a unique number of atoms of each element. Now, we can take this one step further. Oops, one moment. Now, since each compound has a specific whole number amount of atoms of each element, and all samples of the same compound have the same number of atoms of each element in their formula, we know as a result, all samples of a compound have the same ratio of atoms of each element. Now, this is important because no matter how many molecules of a compound we are handling, the ratio of atoms of each element in that molecule remains constant. On top of that, since atoms have mass, the ratio of the mass of each element is constant for the same compound. So let's look at an example. So in carbon monoxide, we have 1 carbon atom for every 1 oxygen atom. In terms of masses, we'd have the following mass ratio shown here. So the ratio of atoms is the same for the same sample of carbon monoxide. So if we scale this up and we look at a very large number of molecules of carbon monoxide, we know that we have 6.02 times 10 to the 23rd carbon atoms over 6.02 times 10 to the 23rd oxygen atoms. And this just simplifies to 1 to 1. So is our ratio of atoms the same, even though we're looking at a very large number of carbon monoxide molecules? Is our atom-to-atom ratio the same for this same compound? Is it the same for this same compound of carbon monoxide? Yes, it is. Further, is the mass ratio also the same for these 2 samples of carbon monoxide? Is the mass ratio for each of our elements the same? Yes, it is. And we can utilize this fact in order to figure out the mass of one element in a compound given the mass of another element in that compound. So let's talk about how that works. And to do that, we're going to do a guided example. So in a sample of magnesium oxide, there are 16.89 grams of magnesium per every 11.11 grams of oxygen. Now it's asking us what mass of oxygen would there be in a sample that contains 2 grams of magnesium. So in effect, we're doing a unit conversion. We're going from grams of magnesium to grams of oxygen. And in this case, our conversion factor is our mass to mass ratio. So if we start with 2.00 grams of magnesium and we're going to grams of oxygen, what units need to be on top? And this is where the unit analysis really demonstrates its utility. What units do we want on top if we're going to grams of oxygen? Grams of oxygen. Right? So we put our 11.11 grams of oxygen on top. And what units do we have on the bottom? What units do we have on the bottom to get rid of the grams of magnesium? The grams of magnesium, exactly. This gives us 16.89 grams of magnesium. Our grams of magnesium cancels, and we're left with grams of oxygen. So let's punch that into our calculator really quickly. So we have 2.00 times 11.11 over 16.89. And that in turn gives us 1.31557 grams of oxygen that we round to 3 Sig Figs, so 1.32 grams of oxygen. Any questions on this example? Any questions on this example?
Yeah, why is there 3 Sig Figs? Is it because of the 2.00 grams?
Yep, exactly. Our input has 3 Sig Figs, so our output is constrained to 3 Sig Figs. Exactly right.
Okay, so how would we know which one we're taking?
For multiplication, you care about the least number of Sig Figs among all the values that you're multiplying and or dividing.
Okay, so it just happens to be that one. So if any of the other values was less, then we would take that one?
Yes, if any of the other values had less Sig Figs, we would take the least number of Sig Figs.
Okay.
Mm-hmm. Any other questions for this? If not, let's now work on the following problem-solving session where we're dealing with a sample of nitrogen triiodide. This is Canvas quiz 2.15.
So the first number that you're multiplying by the fraction, that's what is present in the sample, right?
Yes. Yep, that's the mass of magnesium present in our sample, and we're using the ratio of oxygen to magnesium to determine the mass of oxygen in our sample. Yeah. Does that make sense?
Yeah, so for this one, then it would be 50.76 grams of iodine times whatever else that the sample has, correct?
Yep, exactly. Well, times the ratio of nitrogen to iodine. So let's spend about another 2 to 3 minutes working through this problem, and then we'll come together as a group to discuss. Make sure to provide your responses either via Canvas or via the Zoom chat function. Let's try to get a few more responses and we'll discuss in a few minutes.
The answer that I got is different from the one in Canvas.
Let me check really quickly what it's saying in Canvas.
Yeah, I got 1.9 and Canvas is 1.7.
Let me adjust the range for that. One moment. There we go. I didn't set the permittable range far enough. Sometimes I enter a number and give a little bit of range to account for drift during calculations. So I adjusted that in the Canvas quiz.
Okay, thank you.
So I see a lot of reasonable answers so far for this question. So let's take a look at this question and let's work through it as a group. So we know we're trying to go from the grams of iodine, well, in this case, just I, since it's referring to the element, and we're trying to figure out the grams of nitrogen. We know we have 50.76 grams of iodine, and we know that in our sample, there are 5.6 grams of nitrogen per every 152.28 grams of iodine. The grams of iodine cancels, and now all we have to do is enter this into our calculator. So we have 50.76 times 50.76 times 5.6 divided by 152.28, and that in turn gives us 1.866, which we round to 2 Sig Figs, so 1.9 grams of nitrogen. Does that make sense to everyone so far? Any questions on this example? Yep, I corrected that in Canvas. I was trying to set it to catch a rounding error that sometimes happens, but it should be providing feedback that it's 1.9 now. Any other questions I can address? If not, let's continue on to the next topic. And before we just completely tunnel in on this idea of the law of definite proportions, I just want to call attention to an exception in the law of definite proportions, or more correctly, we need to talk a little bit about some edge cases that come up. So the law of definite proportions runs into issues when we start to talk about compounds with the same empirical formula. So the law of definite proportions states all samples of the same compound must have the same ratio of masses of their constituent elements. Now, the book uses mass and atom ratios as an example of this law. However, this is only indicating the empirical formula ratio, not the molecular formula ratio. So what the law of definite proportions is saying is that all samples of the same compound have the same empirical formula, and where the empirical formula is the smallest whole number ratio of atoms of each element in the compound. So to show a case where the law of multiple proportions runs into difficulty is if we look at, for example, nitrogen dioxide, NO2, and we look at dinitrogen tetroxide, N2O4. In nitrogen dioxide, we have 2 oxygen atoms for every 1 nitrogen atom. And in dinitrogen tetroxide, we have 4 oxygen atoms for every 2 nitrogen atoms, which in turn gives us a ratio of 2 oxygen atoms per 1 nitrogen atom. So these two compounds have the same ratio of atoms of each element. Likewise, nitrogen dioxide has 32 grams of oxygen for every 14 grams of nitrogen. Dinitrogen tetroxide has 64 grams of oxygen per every 28 grams of nitrogen, which in turn simplifies to 32 grams of oxygen per 14 grams of nitrogen. So these two compounds have the same ratio of masses, and they also have the same atom ratio. So whenever you deal with ratios of masses, ratios of atoms, we are talking about the empirical formula. These two compounds have the same empirical formula. So if you try to study these two compounds and you try to apply the law of multiple proportions to these two compounds, you would have difficulty distinguishing these two compounds looking at the mass ratios. They have the same ratio of masses and elements. They have a different total number of atoms of each element. But often when we run experiments, we can only really detect mass ratios. So we have to use a few other methods that we'll talk about in later chapters to tell these two compounds apart. Does this idea make sense to everyone? Does everyone notice how ratios of atoms and masses can be the same for certain pairs of compounds? Okay, so let's keep going now. So let's look at Dalton's law of multiple proportions. So this concerns chemical reactivity. So first, atoms react as whole atoms. There's no such thing as half an atom. That doesn't have any physical meaning. Atoms also react in whole number ratios to form compounds. Chemical formulas indicate whole numbers of atoms of each element. And atoms of two different elements may react in different whole number ratios to give different compounds with a unique chemical formula. So for example, if I take carbon and I react it with oxygen, if I take 2 carbon atoms and react it with 2 oxygen atoms, I can make 2 molecules of carbon monoxide. If I changed the ratio of carbon to oxygen and I reacted 1 carbon atom with 2 oxygen atoms, I would generate 1 molecule of carbon dioxide. So notice how, depending on the ratio of atoms that react, we end up with a different ratio of atoms in our product. So we have 2 carbon atoms per 2 oxygen atoms in our product, or 1 carbon to 1 oxygen for carbon monoxide. Well, for carbon dioxide, we have 1 carbon atom per every 2 oxygen atoms. So different compounds have a different ratio of atoms. Does that make sense? So then, each product will also have a unique mass of each element. So for example, to make carbon monoxide, it requires 12 grams of carbon and 16 grams of oxygen to make 28 grams of carbon monoxide. In other words, in carbon monoxide, there are 16 grams of oxygen for every 12 grams of carbon. This mass ratio is unique for this chemical formula. Now, if we compare carbon monoxide to carbon dioxide, in carbon dioxide, we have 12 grams of carbon reacting with 32 grams of oxygen to yield carbon dioxide and a total of 44 grams of carbon dioxide. In carbon dioxide, we have 32 grams of oxygen for every 12 grams of carbon. So, does everyone notice how the mass ratio, the ratio of the mass of each element that reacts, is different for these 2 compounds? The ratio of masses that react is different. Does everyone see that? Okay. So, continuing on with that idea, so let's suppose, whoops, one moment. So let's unpack this step by step. So let's suppose we have a fixed element of 1 element, and it's reacting with another element that we will call B in this case. The atoms of each element in the product depends on the mass of each element that reacts. Now, if we keep the mass of element A constant, so the mass of the first element A is constant, the number of atoms of element A in each product will be constant. Now, depending on the mass of element B that reacts, the number of atoms of element B will be in the product will vary. And the number of atoms of element B in the product is directly proportional to the mass of element B that reacts. So then, what we can do using the law of multiple proportions is show and calculate that if the chemical formula of one product is known, the chemical formula of the other product can be determined. So let's go through this step by step. First and foremost, we know that if the mass of element A, is fixed, the atoms of A in each product will be the same. Now, further, we also know that the mass of element B is proportional to the atoms of B. So then, if we take the ratio of the mass of element B that reacts, that ratio is equal to the ratio of atoms of element B in the product. So then we can solve this equation. To get the atoms of element B in our product. Number 2 is equal to the atoms of element B in product 1 times the mass of element B in product 1 over the mass of element B in product 2. Now, this is almost exactly identical to how we dealt with the law of definite proportions, or the law of definite composition. There's only one thing that you need to be careful about. You need to make sure that a whole number amount of atoms of A and B are reacting. If you get a fraction, you need to multiply the number of atoms of both elements by a whole number. So what do I mean by that? Let's show an example. Let's suppose I do this calculation and I get N, I have 1/2 atoms of N and 2 atoms of oxygen. Let's just suppose I get that. So I obviously can't have half an atom reacting. That doesn't make any sense. So what I'm going to do is I'm going to multiply both of my atoms by a whole number, in which case it's most commonly the denominator. So I'm going to multiply both of these atoms by the smallest whole number, and that in turn can simplify my atom to atom ratio to 1 nitrogen atom and 4 oxygen atoms. So you want to make sure we are dealing with whole numbers of atoms. Does this make sense so far? Any questions? So let's show how this works in practice. Let's look at the following. Let's look at the following example. Oops, one moment. Okay, so let's do a guided example together where we look at the law of multiple proportions for a series of compounds. So in the first example, we have 1.0 grams of carbon reacting with 1.3 grams of oxygen to generate 2.3 grams of carbon monoxide. Wonderful. Okay. So we know we have 1 carbon atom and we have 1 oxygen atom. Just looking at the formula here. In the second case, we have 1 gram of carbon reacting with 2.6 grams of oxygen to yield 3.6 grams of carbon dioxide. In this case, we have 1 carbon atom, and for oxygen, from our formula, we have 2 oxygen atoms. So then we can clearly see that if we take the ratio, carbon is fixed, so we have the same mass of carbon, ergo we have the same atoms, right? 1 gram, 1 gram, 1 carbon atom, 1 carbon atom. Now let's look at the oxygen atoms. In the first case, we have 1.3 grams of oxygen per every 1 oxygen atom. In the second case, we have 2.6 grams of oxygen per 2 oxygen atoms. And what we can see is that these two ratios are exactly identical. In other words, the ratio of masses, so if we take 2.6 grams of oxygen over 1.3 grams of oxygen, that's equal to our 2 oxygen atoms over 1 oxygen atom. So this ratio is equal, and they cancel out to 2 is equal to 2. So this reaction scheme obeys the law of multiple proportions. Does that make sense so far? Can everyone see how the law of multiple proportions is followed? Any questions so far? Okay, so now from here, when 1 gram of carbon is combined with 3.9 grams of oxygen, we get an unknown compound, and we're asked to figure out what is the formula of the unknown compound. So we know previously that 1 gram of carbon leads to 1 carbon atom in our product. So then we know at the bare minimum, we definitely have 1 carbon atom in this unknown product, right? For our second case, we're going to look at the atoms of oxygen in our unknown over the atoms of oxygen in carbon dioxide, and that is equal to the grams of oxygen in our unknown over the grams of oxygen in carbon dioxide. So solving this equation, we see the atoms of oxygen in our unknown are equal to the grams of oxygen in our unknown, in which case the grams of oxygen in our unknown is 3.9 grams of oxygen over the grams of oxygen in carbon dioxide, which is 2.6, times 2 oxygen atoms in carbon dioxide. Our grams of oxygen cancels, and if we punch this into our calculator, the atoms of oxygen, whoops, one moment. The atoms of oxygen in our unknown is equal to 3 oxygen atoms. So this compound would have the formula of CO3. Does this logic make sense to everyone? Does this problem-solving scheme make sense? Does everyone see how the law of multiple proportions functions? Any questions on this example?
Yeah, I don't understand this one.
Is there a part that I can elaborate on?
Let's see. So that's a formula, atoms of oxygen of unknown.
Yep.
Okay, 0 over, what's the, where do the 20 atoms come from?
Oh, that's
that
that's not a 0. That's an O.
Okay, wait. So okay, so 2. Okay, where did the 2 come from?
In carbon dioxide and CO2, how many oxygens do we have?
Oh, okay. So we're just.
So essentially what we're doing is we're comparing the mass of oxygen that reacted in these two experiments, and that it's directly related to the atoms of oxygen that end up in our product. And since we know for carbon dioxide, to get 2 oxygen atoms in our product, it takes us 2.6 grams of oxygen that reacts. So when 3.9 grams of oxygen reacts for this unknown compound, we in turn end up with 3 oxygen atoms in our product. Does that make sense?
Okay, so we're just dividing the 3.9 with the answer from the one before?
Yes.
Okay.
Or you can divide by any mass of oxygen that reacted, as long as you know the number of oxygen atoms that ended up in the formula from that reaction. So in this case, we know that when 2.6 grams of oxygen reacts, 2 oxygen atoms end up in our final formula. And that helps us figure out what happens when 3.9 grams of oxygen reacts, how many atoms end up in our formula. Does that make sense?
Yeah, so right here it's just 3.9 times 2 divided by 2.6.
Yep. Mm-hmm.
Okay. Thank you.
So let's now check to see how comfortable everyone is with these calculations by working on and opening up problem session 2.16. And I'd like you to tell me the formula of this unknown compound given the following data. And let's take about three to 4 minutes to work through this problem, and then we'll discuss momentarily. And don't be shy to submit your responses via the Zoom function or the Canvas quiz feature, or ask questions in the chat or verbally. And we'll discuss in about 2 minutes. Let's try to get a few more responses in the chat or via Canvas before we discuss. Any questions so far? I'd like to see a few more responses via Canvas or in the chat before we start our discussion. If not, we'll discuss in approximately 1 minute. Okay, so let's discuss the following problem. So first and foremost, for our known sample, in our first run, we have 30 grams of, we take 14 grams of nitrogen reacting with 16 grams of oxygen to generate 30 grams of nitrogen monoxide. Okay, in our second experiment, we take 28 grams of nitrogen with 16 grams of oxygen to generate 44 grams with the formula that's unknown. So our first step is to identify our element with a fixed mass. So we see clearly in both runs we use the same mass of oxygen. So then the number of oxygen atoms is tentatively going to be the same. Next, we compare our variable mass element. So in our first example, we have 14 grams of nitrogen. In our second example, we have 28 grams of nitrogen. Let me reverse it so it's easier to solve. So we have 28 grams of nitrogen in our second case and 14 grams of nitrogen in our first case. And this is equal to our ratio of atoms. So we have the atoms of nitrogen in reaction number 2 over the atoms of nitrogen in product 2 over the atoms of nitrogen in product 1. And how many atoms of nitrogen are in our first reaction product? How many atoms of nitrogen are in our first reaction product? How many atoms of nitrogen are in nitrogen monoxide? Just 1. Okay, so as a result, after solving, we get our number of nitrogen atoms in product 2 is equal to 2 nitrogen atoms. So in turn, that would give us a formula of N2O, or dinitrogen monoxide. Does this example make sense to everyone? Any questions on this example?
Sorry, could you explain again how you got the 2N for the product of the second one?
So the ratio of masses of nitrogen that reacts is equal to the ratio of atoms in our product. So we have 28 grams of nitrogen that react to generate our unknown, and in our known nitrogen monoxide, it takes 14 grams of nitrogen to give us 1 nitrogen atom in the product. So now that we have this equation set up, all we have to do is move this term to the right, and we end up with 28 over 14, which simplifies to 2 nitrogen atoms. And we got the 1 nitrogen atom, yes, because nitrogen monoxide only has 1 nitrogen atom. That is correct.
Thank you.
Yep. Does this make sense? The 30 and 44 grams are not needed for this problem. Exactly. Yep. Any other questions I can address? If not, let's try another example just to make sure everyone's comfortable with this idea, as the logic associated with the law of multiple proportions can be applied to other formula ratio problems. So I'd like us to work on problem solving session 2.16.1, and this is in Canvas quiz 2.16. This is concerning the reaction to make acetylene versus the reaction to make ethylene. And we'll discuss in about 2 to 3 minutes. And don't be shy to submit your responses via Canvas or via the chat function. And don't be shy to submit your responses in the chat or via the Canvas quiz feature. Let's try to get a few responses before we discuss this next problem. And I would check that you have your atom and mass ratio set up in the correct order. I suspect you have the atom and mass ratio reversed. And we'll discuss in about 30 seconds to a minute. Let's see if we have a reasonable pool of responses. We have a few responses, but I'd like to see at least 1 to 2 more in the chat or via Canvas before we discuss, just so that way we're getting value in practicing these problems. So let's discuss this example now. So for acetylene, we have 2 hydrogen atoms plus 2 carbon atoms, leading to C2H2. This requires 2 grams of hydrogen and 24 grams of carbon. Okay. So for ethylene, we have 24 grams of, let me write this so it's a little more symmetrical. We have 4 grams of hydrogen reacting with 24 grams of carbon to yield ethylene, which is C2H4. Oh, sorry, from nomenclature. Let's now try and figure out the formula of ethylene using the law of multiple proportions. So first and foremost, we see that the mass of carbon is the same in these two trials. So the atoms of carbon in our product will be the same. So both of these compounds have 2 carbon atoms. Now let's figure out the number of hydrogen atoms. So we know that in our second trial, we have 4 grams of hydrogen. In our first trial, we have 2 grams of hydrogen. This mass ratio, the ratio of masses of each element, is equal to the ratio of atoms. So we do not know the number of hydrogen atoms in product 2, but we do know the number of hydrogen atoms in product 1, which is acetylene, so which is 2 hydrogen atoms. So then if we solve this equation, the number of hydrogen atoms in product 2 is equal to 2 times 2 hydrogen atoms, which gives us 4 hydrogen atoms. So ethylene has the formula of C2H4. Does this make sense to everyone? Any questions on this example? Any questions? If not, let's continue on. We're almost finished with this chapter. We can summarize all of our discussion of atomic structure and reactivity into Dalton's atomic model, which states matter is composed of indivisible particles called atoms. So if we look at bulk matter, we can break it down into indivisible particles called atoms. Atoms of the same element are alike in mass, size, and properties. Atoms of different elements have different masses, sizes, and properties. So for example, a carbon atom has a mass of approximately 12 AMU, while an oxygen atom has a mass of approximately 16 AMU. Further, each of these atoms have dramatically different reactivities and react with other elements and compounds in dramatically different ways. We've discussed previously that atoms combine to form compounds in whole number ratios. So for example, 1 carbon atom reacting with 1 oxygen atom to generate carbon monoxide. There's no such thing as half an atom. An atom loses its properties and reactivity if you cut it into its component particles. So atoms of 2 elements may combine in different ratios to give different compounds. So for example, 1 carbon plus 1 oxygen atom will yield carbon monoxide. 1 carbon plus 2 oxygen atoms will yield carbon dioxide. Different ratios of atoms, different product compounds. Further, the same compound will have the same number and ratio of atoms of each element, and the mass of each element in the same compound is identical. So for example, if we're looking at nitrogen monoxide, it will have 1 nitrogen atom per 1 oxygen atom, and it will also have 14 grams of oxygen for every 14 grams of nitrogen per every 16 grams of oxygen. Regardless of whether you're looking at 1 molecule or whether you're looking at, for example, 2 molecules, the ratio is still the same. 2 nitrogen to 2 oxygen is equivalent to 1 nitrogen over 1 oxygen. So the ratio of masses of each element and the ratio of atoms of each element is fixed for the same compound. Finally, atoms cannot be created nor destroyed. In chemical reactions, atoms are rearranged. This just summarizes all of the rules and laws that we've discussed so far in this chapter. The last thing we're going to do is we're going to close out with a discussion of chemical formulas. We've already been applying aspects of chemical formulas in our discussions already, but this is an important skill that we want to develop before we start to discuss chapter 3. So chemical formulas, quite simply, specify the number of atoms of each element in a molecular compound. So the subscript can indicate the number of atoms of that element. So in calcium chloride, yes, we'll talk about lab 2. Essentially for lab 2, we'll discuss and record that. And we'll talk about that once we're finished with this section. All the labs will be recorded for your reference. After that question was addressed, so looking at calcium chloride, how many chlorine atoms do we have? How many chlorine atoms do we have? 2. So we have 2 chlorine atoms because we have a subscript of 2. Subscripts can also indicate the number of polyatomic subunits or ions. So this 2 applies to all species in the parentheses. So in calcium nitrate, we have 1 calcium atom and 2 nitrate polyatomic ions. So after drawing a picture, how many calcium atoms do we have? How many calcium atoms do we have?
1.
1, yep. Okay, and how many total nitrogen atoms do we have? 2, yep. And how many oxygen atoms do we have? 6, okay, perfect. So now let's look at our next guided example. In this next guided example, we're going to indicate the number of atoms of each element in each formula. So in this case, aluminum hydroxide, I apply my subscript to everything in the parentheses. So I draw out my 3 hydroxides. So I have 1 aluminum, 3 oxygen atoms, and 3 hydrogen atoms. In sodium carbonate, I have 2 sodium atoms, 1 carbon, and 3 oxygen atoms. Does this example make sense so far?
Yes.
So then, for our last example for today's lab lecture, I'd like you to open up problem solving session 2.18, and I'd like you to indicate the number of atoms of each element in each of the following formulas. Okay, I see a lot of reasonable responses already, but I'm gonna have to ask everyone in the chat for some help. So I'm gonna apply my subscript to everything in the parentheses. So I have 2 nitrogen. Oh well, let me draw out my ammoniums. And then we have sulfate. So how many total nitrogens do we have in the first example? How many total nitrogens do we have? 2, yep. How many hydrogens do we have?
8.
8, yep. We have 1 sulfur and 4 oxygens. Perfect. So for magnesium phosphate, we apply our subscript to everything in the parentheses. So we have our magnesiums, and then we have 2 phosphates. So how many total magnesiums do we have?
3.
3, yep. How many phosphorus atoms do we have?
2.
And how many oxygen atoms do we have?
8.
8, yep. Perfect. This is something we'll be doing a lot the next chapter when we focus on naming compounds. So this concludes our lecture session, our supplemental lecture session for today. So let me stop the recording.